what is arc length or distance traveled as an integral? When we think of trying to find the arc length of a curve, there's two settings where it's done. The first setting is where you've got the graph of some function. Y equals f of x over some interval x going between a and b. You could pretend that's a piece of string. In trying to find its arc length, what you're trying to find is you're imagining you can make the string straight. Don't stretch it though, don't overstretch it. Just make it straight, just barely. That is the length that you're after. The approach, just like with volumes, is to slice into little tiny pieces. But this time, your slices aren't necessarily vertical or horizontal. And this is where it gets a little funny, is like, how do you do this in the right way? You're slicing just into little pieces, like near that point right there, at some value of x, until the graph looks almost straight. That's local linearity. We know for smooth graphs that don't have any corners in them, for example, that when you zoom in near any point, the graph looks straighter and straighter. Local linearity. You pretend you've gone in so far that it really is indistinguishable from a straight line. Maybe it's slightly curved, but maybe you can't tell. And you say, I'd like the length of that line. S is, unfortunately, perhaps, the standard letter to use for length of a curve, arc length. S is arc length. It does not mean speed. It means arc length, unfortunately. So if we're looking at a little piece of it, we are asked after the small arc length, maybe we want to call it delta S. Hint that it's a small amount of arc length. Again, it looks straight, but maybe it's slightly curved. You could draw in what would be approximately a right triangle. We want to relate this to the function itself. A salient feature to look at it with the function here is the slope. Slope would be delta y over delta x. And the Pythagorean theorem applied to this approximate right triangle would say that delta S is approximately the square root of delta x squared plus delta y squared. It'd be exactly equal if it were an exact right triangle. Then you do a bit of trickery. You write delta y squared as, well, delta y squared over delta x squared times delta x squared. Just a trick there of multiplying by 1, delta x divided by delta x, assuming delta x is non-zero. For what purpose? For the purpose of rewriting this expression in a way that's going to ultimately give me a Riemann sum. I'm going to factor out the delta x quantity squared out of both terms. It's there in both terms. It's here in the first term and it's here in the second term. Factor it out. On the first term, you're left with the 1. On the second term, you're left with this fraction. The ratio of two squares is also the square of the ratio. I'm factoring the delta x squared out of that, so I need it there. And then, if I assume delta x is positive at least, the square root of delta x squared will be just a plain old delta x. In general, the square root of something squared is the absolute value of that something. But that'll be the something itself if the something is positive. Let's go ahead and make that assumption. Could you do this when delta x is negative? Yes, but Let's just keep it simple. Let's do it when delta x is positive. The Riemann sum then for the entire arc length of the entire curve initially would look like that. And then upon substitution, you get that it's approximately the sum of these things. And notice that delta y over delta x, when delta x is small, is close to the derivative. So go ahead and make that replacement too. That'll be true when delta x is small. We'll get a good approximation. Why? You might remember from calculus 1, I hope, that the derivative of a function at a point x can be thought of as a limit of a difference quotient. Usually we call the letter that is going to 0 h, but it doesn't hurt to call it delta x. It's a rise over a run. F of x plus delta x minus f of x, all divided by delta x. And this thing on the top here, that's a change in y. That's a delta y. So I did two approximations here, really. One of the approximations comes from this approximation for delta s. And another one comes from replacing delta y over delta x with dy dx. With function notation, instead of dy dx, you write f prime of x. Then you say, hey, that looks like a Riemann sum for this function in front of the delta x. Let delta x go to 0. The total arc length is the integral of square root of 1 plus f prime of x squared over whatever interval that we're talking about. In this case, x goes from a to b. Is there an infinitesimal version of this? Yes, there is. The infinitesimal version is effectively the same thing, except all the deltas become d's and all the approximately equals to's become exactly equal to's. Starting up here, replace those deltas with d's, replace that approximately equal to with an exactly equal to. You could say ds is square root of dx squared plus dy squared. Same kind of trickery as before, allows you to write that like this. Not using parentheses here, but I could, maybe I should. Factor out the dx squared like this. Assume dx is positive, rewrite it like this. Put the dx out there. And then s itself is going to be the summation of those ds's, the summation of this stuff. But to actually do it, you have to do a definite integral. Saves a tiny bit of time, I guess. Also is just maybe a little bit more fun because you're not thinking about Riemann sums, which are always kind of a pain to think about.